So yeah, my name is Vincent, and this work is co-authored by David Folch, who's sitting over here. And we're both affiliated with Northern Arizona University. David is an associate professor in the Department of Geography, Planning, and Recreation. And then I'm currently a grad student enrolled in the data science program at NAU. I'm here today to present our current methods for modeling outdoor recreation across the state of Arizona. We're primarily using linear data from social media apps in combination with more traditional GIS data sources. This is a work in progress. We've been doing this for close to a year now, but we would appreciate any of your feedback or insights as we look to refine our methods moving into year 2. So the state of Arizona is currently interested in locating and cataloging abandoned mines. These abandoned mines pose 2 primary risks to the population. The first would be chemical risk to public health, and this is folks living near an abandoned mine. They may be chronically exposed to toxic byproducts of the mining process, things like arsenic, lead, or mercury. And then the second risk, which is the focus of this presentation, is the physical danger that an abandoned mine poses to the public. Vertical mine shafts are often deep enough to trap, injure, or kill anyone who is unlucky enough to fall into them. Arizona has a lot of rural and open space, but as cities continue to spread and outdoor recreation continues to become more popular, there is a need for the state to identify which mines pose the most risk and then rank them for remediation. And a project of this scale requires a multidisciplinary approach. This project is a collaborative effort across all 3 Arizona state universities. And each team is bringing their own unique expertise to the project, such as biology, geology, GIS, or remote sensing. And then demographics is our area of focus. And I'm working to map the residential population of the state using census and parcel data from each county. And then the focus of this presentation is the model we're working on to map recreation across the state. And all of our work will factor into a final risk assessment that will rank each of the mines by the level of hazard that they pose. And we do hope this research enables state officials to utilize remediation funds to greatest positive effect for both the environment and residents of Arizona. So for the rest of the presentation, I'll focus on our current methods of modeling the recreational presence. And yeah, this is just going to be one of the factors that play into that final risk analysis I just talked about. So recreation extends human presence beyond the borders of towns and cities into the more remote areas of Arizona where abandoned mines are located. And the assumption that we're making is that more people means higher potential for injury from either accidental or intentional interactions. Intentional interactions such as adventure seekers bringing in equipment to rappel into mines and explore them. There are many popular recreational activities in Arizona, but currently we're focused on hiking, biking, and running, as we feel that a model based on these traversal activities will include the points of interest that most destination activities are based around. So like climbing based around rock features, camping would be campsites, and swimming would be around water. And you have to hike to get to any of those usually. And then later in the project, we also have plans to model hunting and then off-roading, as we believe those activities are unique enough to require their own models. And we've built our model on 3 inputs. The first is presence data, and this is coordinates of confirmed recreational presence. There were several apps and websites that we initially considered to get this data from, sites like Flickr, Twitter, or Google. But we noticed the availability of geotagged photos has declined in recent years as users have opted for increased privacy. And when photos are tagged to a location, they're tagged to points of interest, and that can often represent broad areas of presence. So to use an example from the town I'm from in Flagstaff, there's Humphreys Peak to the north. And so if someone were to tag that photo, they might be on the peak itself, or they could be taking the photo from the Weatherford Trail to the south, or from Lockett Meadow to the north. And that fuzziness is why we moved away from point of interest data in general. And as far as official sources go, the best that we have so far would be annual visitation numbers for national and state parks. But those are large areas without internal presence detail. So we ended up deciding on the linear data from AllTrails and Strava. These are the most popular apps that we could find that also had access to their data. And so that does make this a convenience sample. It's not a true random sample of recreation across the state. And then the second input that our model needs is background locations. This is a grid of pseudo-absence points, and we derive these from geospatial raster coordinates. The number of points will depend on the scale that we're processing at. And then the last thing that our model needs are explanatory variables. I've grouped them here into 3 categories. So first is activity. So we assume people access recreation via cars, and so traffic counts can measure human activity better than like a traditional residential population density from the census. And then we also have included some park visitation features. And then accessibility will help define how much vehicle access a given location has. And this depends on the type of road, including dirt roads, and the quality of the road. And then lastly, we have variables that we believe contribute to the attractiveness of recreational points of interest, such as interesting terrain, water features, and vegetation. So our model faces two challenges. We don't have any access to absence data, and our presence data is a convenience sample, not a systematic random sample. Maxent was developed by ecologists who face these same challenges when trying to estimate species presence. And this is a logistic regression model, so it places more importance on presence than absence, since the absences are unknown. And the model uses elastic net regularization, which is a hybrid of lasso and ridge regression. This works to eliminate unnecessary variables and minimize autocorrelation. The data used in the model is aligned based on geographic location, but the model itself does not consider the geographic relationships like distance decay or proximity. And the strength of this setup is that once the model is trained, it can predict at any geographic location where the explanatory variables are available. So now, for the next few slides, I'm going to discuss our actual implementation process. We'll start with this slide here, just to highlight a few of the packages that we used. So I'm assuming for this audience, everyone knows about NumPy and SciPy. But the relief visualization toolbox was a specialized tool that we used to compute slope and sky view factor, which is it's a measure of horizon visibility, how much horizon you can see from a given point. And then GeoCube was used to convert vector data into raster data. Rio X-array combines rasterio and X-array for geographic raster analysis. And then GeoPandas is a combination of Shapely and Pandas for geographic vector analysis. And lastly, all this feeds into ArcPy, which is a proprietary general spatial analysis package from the Esri Corporation. They also produce the ArcGIS software. So first step in creating presence data for us was to gather linear data. AllTrails does not currently have an API, but they did allow us to manually download trail geometry, and average ratings, and the review counts for all those trails. So we were able to collect all 3,000 of their curated trails. Strava has a really good API. It still presented us a few challenges, though, when we tried to collect all the segments in Arizona. So the search query is based on a bounding box, and the bounding box will return a maximum of 10 segments. The start and end point of those segments need to be contained within the bounding box. So the best idea I could come up with was to use recursive subdivision. So I will run the query on an initial bounding box, and if it returns 10 segments, I'll store those segments, and then subdivide the box and call the query again for each of the child boxes that has 10 segments. And that recursion will continue until fewer than 10 segments are returned. So in this example, 3 of those boxes would be done, and the upper right-hand box, we must continue to subdivide that one. And then we'll keep going until all of the boxes have returned fewer than 10 segments. This strategy does not solve all the challenges with the API, though. First, we don't know the total number of segments in Arizona, and these boundaries that are created by the subdivision process can split segments, and that'll prevent them from being returned by the search query. So we need to be searching efficiently while still searching the same area multiple times with different boundaries, and that's a bit of a balancing act. So to fix this, we created an initial search pattern by randomly scattering 50-kilometer boxes across the state in a way that covers the state in the least amount of boxes, while still allowing for overlap across the boxes. This results in around 110 initial search boxes, and it takes about 2 weeks to process due to API limits. But then when we finish that, we'll repeat the process with a new set of random search boxes or another seed. We still, though, we can't be sure that we have all the data from the state. So far, we've gathered 20,000 bike segments. And next, we need to convert this linear data to presence points for Maxent to use. And the lines on the right represent real-world challenges of double counting that we need to deal with. So, for example, AllTrails represents out and back routes with parallel line segments. So that line up at the top there, the out and back parts of the segment are offset from each other by several meters. And then in Strava, users are allowed to create as many unique segments as they like, so long as they're not identical to another segment. And this tends to result in numerous overlapping segments on popular roads and trails. It's kind of represented by the green lines there. And then intersecting trails and the zigzag trails will make when there's a switchback. That'll result in higher trail density, which can lead to spatial bias. And we address these challenges using rasterization. So looking at the example on the right, we'll lay a raster over the trails, and all the intersecting cells are marked as presence, which will be represented by the yellow dots. And this will solve our double counting and density problems, as any cell not intersected by a trail will be marked green, which represents pseudo-absence. And that'll result in our binary dependent variable that our model will use. This also results in evenly spaced presence and pseudo-absence points. And as we'll show in a few slides, this method also allows us to aggregate any attribute from the source lines to the target points. I should note, though, that this process shifts all the intersecting presence coordinates to the centroids of the raster cells. And that does reduce the accuracy of our original presence locations. However, the data from AllTrails and Strava is a bit fuzzy. Strava will snap its users' movements to existing segments within a gap threshold, and we're not sure how far that threshold is. And AllTrails users can also suggest and make trail edits, and we're not sure how those edits are moderated or verified. And then neither app appears to be map matching their lines to the centers of roads or trails in their underlying base maps. And currently the scale of this grid here is at a raster size of 222 meters. In the future, we'll reduce this to improve that accuracy I was talking about. So the rasterization process on the previous slide also addresses our need to spatially thin our data. If presence data is overly clustered, like from switchbacks or trail intersections, it can cause spatial bias where the model overfits on clustered presences. So thinning the data will reduce those clusters. It'll also give us more control over the presence to pseudo-absence points, the ratio between them, and that's useful for model optimization. And then in our case, we have hardware constraints to deal with. The computers we're using can only handle around 6 million points, and that's another reason we use the 222 meter scale raster. Once we get access to better hardware, we'll test at higher resolutions. So now let's transition to the creation of our explanatory variables. So we applied the same trail rasterization process to waterways, major roads, and access, which are all linear data sets. Since Maxent does not take proximity into account during model training, we need to create distance decay rasters that spread the impact of each line across the study area. To do this, we use Gaussian filter functions from SciPy. And I had previously encountered the Gaussian blur in digital art software like Photoshop or Blender, so it was fun for me to use those underlying concepts spatially in our project. So to start with major roads as an example, we downloaded daily traffic counts from the Arizona Department of Transportation, and then we rasterized the traffic counts so that if two roads intersected the same cell, both the counts are added together to preserve the total counts from the original data. And then using the Gaussian filter, we could spread the traffic counts out spatially and create sort of a traffic score for nearby cells. And we care about the relative values of these cells, not the actual magnitude of that score. And then for this, we used a standard deviation of 10 kilometers. And then for the other two, for access and waterways, we used a standard deviation of 1 kilometer. And for all three of those, we truncated the Gaussian blur effect after 3 standard deviations. And in the future, we're considering not truncating at all to spread the impact across the whole raster. So the remaining explanatory variables were created from official raster sources. And I obtained the digital elevation model from the US Geological Survey. The DEM was processed to create slope and skyview rasters, which help identify interesting locations in the landscape. And then I used Google Earth Engine to create a vegetation raster from Landsat satellite imagery. And then all of our climate data is coming from Oregon State University's PRISM data set. So that would be our temperature and precipitation data. And then our target raster is based on the DEM. It was already in our desired coordinate reference system, and it's also the highest resolution raster, around 30 meters. And so due to the computational constraints, we had to aggregate 64 cells up to that 222 meter raster scale. And go over a little bit of that here. So different strategies are needed when matching a source raster to a target raster. So if the source and target rasters are already aligned, then you only need to aggregate from smaller to larger cells, and that's a simple average of the source cells. But if the source and target rasters are not aligned, then during the aggregation process, an area-weighted average of the source cells is used instead of a simple average. And then when going from larger to smaller cells, as in the case of our PRISM data, bilinear interpolation is used to estimate new values of each target cell based on the distance-weighted average of the 4 nearest source cells. And at this point, our dependent variable and 10 explanatory variables are processed. So we'll join them together into one table aligned to the 182,000 presence and 5.8 million pseudo-absence points, the grids that those make. And then in order to run this model on our current hardware, we've recast the field data types as uint16 instead of float64, and that helps reduce the memory footprint. And then in addition to that, in order to allow for nonlinear relationships, we include several transformations of the explanatory variables in the model, including quadratic, pairwise product, and the smooth step function. I'll take a moment here to a little water, and then we'll talk about the results. So this is currently our best performing model as far as area under the curve values go. The cell values in this map of Arizona range between 0 and 1. The brighter areas are where the model is predicting higher likelihood of recreational presence. And we're using all 10 of our variables in this model. Just a quick review here. The road traffic is a rough way to quantify the dispersion of human activity across the state. A road access is a practical indicator of ability to reach backcountry areas. Slope, sky view, and water access are indicators of recreational attractiveness. And then we've included 2 indicators from our official parks data. And greenness, precipitation, and temperature are our ecological indicators. And to quickly orient you to this map of Arizona, the large donut in the center, that's Phoenix. The dark center of that is the urbanized area of Phoenix. The smaller donut to the southeast is Tucson. And then the 3 bright spots north of Phoenix are Prescott, Sedona, and Flagstaff. North of that, you'll have the Grand Canyon, and the dark region in the northeast corner of the state is largely represented by the Navajo Nation and the Hopi Reservation. So in this next one, we took away the 3 ecology variables, and you may have to squint here to see the difference, but in general, it brings more nuance to the map. It's most noticeable in the northeast part of the state. And then this third map, this one happens to be our favorite visually, but we've removed the parks variables, so that removes any land use factors from the model. And so you can kind of see here we gain even more nuance across the state. And then lastly, just for the comparison, we did a model on just the ecology variables, which is a traditional starting point for most species distribution models. But it's hard to believe that this is accurately predicting human recreation. Our reasoning behind that is that human recreation doesn't depend on climate in the same way species habitats do. So, we ski where there's snow, and we go off-roading where there are dunes. We can put water in our packs to hike out into the desert and see interesting rock features. And we can also, we can put spikes on our shoes to climb up frozen peaks. And then, we have roads and trails to get out to each of these remote locations. So we felt this ecology-only model doesn't accurately reflect the human ability to interact with our environment. So these are some standard metrics for measuring model performance. So the top row there is our ROC curves. And from left to right, they have area under the curve values of 0.85, 0.83, 0.8, and 0.73. We also present the precision recall curve, since our presence data makes up less than 3% of the overall data. So because of that ratio, we use this. A no-skill model for this ratio of presence to absence points would result in a 0.015 area under the curve value. And our model's values from left to right here are 0.18, 0.17, 0.15, and 0.09. You can see here the baseline is performing the best by these metrics. The second and third model are close to it. The ecology-only model is definitely the worst of these. So we have some interesting challenges with this project because we can't just rely on those area under the curve values. We know some truthy things about the state of Arizona and visual cues that hint we're moving in the right direction. So if we look at this prediction of the Grand Canyon, the light gray line, just to orient you real quick, that light gray line in the middle there is the Colorado River. And we do know from the park data that the north rim of the canyon gets less visitation than the south rim. And in this aspect, the model is performing well. It's identifying the north and south rim of the canyon. And then another positive visual indicator is that our model is predicting the hiking areas in Phoenix while masking out the urbanized areas. We like this because we want a map of recreation, not population. And there's also some negative indicators from other models. So the ecology-only model here, you'll see that as we start to introduce the climate data, the model wants to predict the north rim as higher than the south. It's lush with vegetation and gets more precipitation than the south rim, but we know from park data that the south rim definitely gets more visitation. Another negative indicator is here where the model is predicting the urbanized areas of Phoenix with a high likelihood of recreation. And then lastly, here's an interesting case of the baseline model counterintuitively classifying regional parks with a lower likelihood. You can kind of see that polygon there. That's the boundary of a park that's been given a lower likelihood. That's one of the reasons we are not happy with our current parks layers. So we want to achieve the highest area under the curve score that we can, but we also want to be critical and create a model that qualitatively fits what we know about recreation in our state. A quick summary just to remind you here, the big picture of this project is to rank abandoned mine sites for remediation, and human presence is one contribution to that final ranking. And as I've showed you today, we have to make quite a few modeling decisions, many of which we're still working through, and we plan to consult with domain experts to make further refinements to our methods. The two main types of diagnostics we're considering in analyzing our model are the traditional machine learning metrics of area under the curve values, and then more qualitative analysis of the mapped predictions, so those visual cues that I was pointing out. And now that we have an initial model, we want to run extensive sensitivity analysis to gain a deeper understanding of the effects each of our inputs has. So I plan to gather a few more obscure presence data sources like trail forks, which is mostly about mountain biking. I believe now they're owned by Strava. And then as well as iNaturalist, which is a birdwatching app. And then I would like to spend some time revising our explanatory variables, so testing different distances in our Gaussian blur process. And I'd also like to add a redness layer to help identify rock features. I'm hoping that's going to balance out some of the effect of the greenness layer in regards to that north and south rim of the Grand Canyon. We're also working to get access to more powerful hardware that'll allow us to run this analysis at higher resolution, which we hope will improve the model as those presence points get closer to their original position. And we will also test other models. Random forest is the first on our list, and the way we've set this up as a unified table will allow us to quickly do that. And then lastly, we're going to build some other models based around motorized recreation and hunting. We're currently working on a partnership that will grant us access to some of that data. So that's all I've got for you today. I've listed here mine and David's contact info in case that's easier than reaching out to us over Slack. So I think now it's time for questions.
Thanks so much, Vincent. Do we have any questions for the speaker?
Yeah, great talk, Vincent. I was curious, when you were doing the rasterization to eliminate the overlap with the line segments, did you consider at all using the Uber's H3 hexagons for that instead of simple rasterization?
Yeah, we have looked at that system, and we're still not sure what the final output of the whole project will be, but we are considering using that system instead of just a simple grid. So we are considering that, and we'll keep that in mind.
Great. We have a question on the Slack from Steph Buongiorno. One question is, have you explored data from sources like Hiking Project or Mountain Project? mountain project is like all trails, but for climbers?
Yeah, we did consider that. Don't think they currently have an API, but from what I've looked at, the website could be scraped to get a lot of the same information that we have. So that may be something we do in the future, because it would be specific to climbers. And I think they have a couple of other sites that even like kayaking and some other activities that are more obscure as well. So we might do that in the future.
We have another question here. Can you talk to us more about how predicting backcountry population has a relationship with the work on determining the risk of abandoned mines?
Yeah, so other teams are focusing on identifying the mine locations, and there's a ton of work involved in that. The existing mine locations are spread across several different data sets, and so those all need to be brought together, as well as, they're going to try to use some machine learning methods to identify undocumented locations. So that work will be kind of pointing out where the abandoned mine locations are, and then what we're trying to do is provide the estimates of kind of where people are in relationship to those mines, and in hopes that that'll help the eventual risk analysis. So if we know where the mines are and we know how close they are to people, whether that's residences or where people are recreating, and that'll allow them to kind of rank mines against each other as far as the risks they pose.
Just add a couple things, they're also looking at biology, are these abandoned mines being used by bats and other animals? And so there's a ton of different metrics that they're being used in the analysis to try to figure out what the priorities are going to be across them. The demographics is just one of those cases.
Any other questions from the room? I'm just trekking over, excuse me.
Thank you very much. I really enjoyed your presentation. I'm curious about the ROC curve slide, if we could go back to that page.
Yes.
And I think this just belies my ignorance about your scientific method precisely, because I'm curious what you are measuring with the ROC curve, what prediction metric is being performed. My mental model of what you're doing, and I'm asking you to correct me, is that you are building a raster of essentially floating point predictions for each 222 meter grid square over the state of Arizona based on many different layers that are all predictive in some sense, right? You're weighting them and combining them. And then you are comparing that raster, which you have produced, with the presence or absence data from your AllTrails mapping information. And that is where you get your ROC curve, such that for some threshold with each raster layer, that threshold then predicts a mapping, and that's probably in fact what your x-axis is here on the ROC curve, right?
Yes.
Is past that threshold, this many presences from your known map data precisely match what your raster model has predicted. Is that correct?
Yes, that is correct. So that's the true positive rate on the y-axis so it's how fast are we identifying the known presences, and then as we're identifying known presences, kind of how many background points are being classified as presence, and that's what creates the curve there. The ROC curve is the one that can be compared most easily to the other Maxent studies, and that's where the no skill of a 0.5 area under the curve value is the dashed line. So these values are considered, compared to other Maxent studies, these values are decent. The one for the ecology only model, 0.73, that's not a good value. Anything under 0.75 is kind of generally considered to not be great. But this curve also, though, one of the challenges here is that one of the critiques we've seen of using this curve, the ROC curve, is our data the ratio is kind of skewed. So there's very few presence points compared to background points. And that's why we also included the precision recall curve, which kind of better analyzes how the model is performing. So it's the sheer amount of background points can kind of inflate the ROC curve values. And that's, does that help answer your question a bit there? I think you have, yeah. Yeah.
All right, let's thank Vincent again.